Hello, this is Miss Watkins, and today we are going to look at writing and balancing chemical equations. This is one of my favorite things to do in chemistry because it's like a brain puzzle. You get to work your way through equations and decide how to make your values equal out on both sides and follow all the laws that we have talked about prior to this class and we're about to go over as well. What we've learned so far is really important because they all play into the lesson at hand today. The first thing we went over is periodic trends, and this is important because it actually helps us to know if we're making compounds that actually can be formed, and it helps us to know about diatomic molecules, which we have discussed in class. Diatomic molecules, if you remember, are molecules that can come together bound to another of itself. So what I mean with that is like oxygen gas comes as O2, not just O. We've also looked at chemical names and formulas, which is really important because as we practice writing chemical equations and balancing chemical equations, you will have to start practicing being able to write the formulas from given names of chemical compounds and being able to write the correct balanced formula before we can even use it in the balanced equation. So this is some very good practice with that, as well as the law of conservation of mass. This is the most important law that we study in this class, and it comes up very often, especially right now. The law of conservation of mass states that matter is neither created nor destroyed. And why this is important is because it tells us that our balanced equation must be equal on both sides of my reaction. So on my reactant side and my product side. And yesterday we practiced writing word equations. And this is tying into the second bullet, chemical names and formulas, because we were able to put chemical compounds that we were given the name of into formula form and write it as an equation. So this slide from first bullet to fourth bullet goes from what we've learned earliest in this class to what we've learned most recently in this class. So if you have any problems with periodic trends and chemical names and formulas, I would suggest that you go back over those before you continue on to the next part of the lesson. What we get from balancing equations and writing chemical equations ties into a couple lessons that come after this. Excuse me. Types of chemical reactions is what we learn right after this lesson. Usually we will have this lesson and then a day of full practice because balancing chemical equations is something that's very important to this class. So you do have to make sure you know how to do that. So we take a whole day to practice it. But after that, we do types of chemical reactions. And this is important because once you know how to balance them and how to write them, we need to understand what kind of reactions we're dealing with at the time. The math portion of balancing chemical reactions is very important when we talk about moles. And moles is an important mathematical value that we use in chemistry. You're going to end up using them a lot, and hopefully you'll learn to love them just as much as I do because the math in chemistry is a huge part of the class, and it's one of my favorite parts because it's very logical, it's very sequential, and it all makes sense. So I'm hoping that it'll do that to you as well. And once we understand moles and we can convert between all of those units and we understand balancing equations, that will lead into stoichiometry, or stoichiometry as some pronounce it. This is the big math of the class. This is the portion of the class that either you are going to love or you are going to hate, and I hope you love it because I love it and it's so much fun. Which makes me sound nerdy, I know, but it's very fun and I hope that you enjoy it because we will practice moles and stoichiometry a lot in the future. The essential standard NC State standard that we cover in this class is Chem 2.2.3. This is specific to this lesson today, and it's analyzed the law of conservation of matter and how it applies to various types of chemical equations. So just as we reviewed the law of conservation of mass or matter, it's the same law, just depending on where you get your resources from. The standard says matter, our textbook actually says mass. Excuse me. And we're looking at how it applies to chemical equations, how we can use that to make sure our chemical equation is balanced. Because if we don't have a balanced chemical equation, we cannot use it in stoichiometry. Our values will come out incorrectly, and that is not what we want. Okay, so this is the start of the actual lesson today, and we are starting with chemical formulas. We did talk about this a little bit yesterday, so I'm hoping that it still makes sense and that we can tie it into full equations, both skeleton and balanced. So chemical formulas are representative of the actual reaction, and if you see RxN through these notes or any notes that I give you or any websites that you look at, literature, anything like that, RxN is the abbreviation for reaction. So please make sure you have a note of that. Just highlight it in your notes, put a little post-it there. But this is very important for you to know because a lot of scientists use that. We may be smart, but we can also be kind of lazy. So we like to abbreviate a lot of things. So please make sure you know those abbreviations. But they are representative of the actual reaction. So if you look at my next example, I have iron plus oxygen yields, or arrow, iron 3 oxide. So this is a word equation because I've given you the words or the names of your chemical compounds. When we look at chemical formulas, we now want to switch to formulas. So we want the formula for iron plus the formula for oxygen yields the formula for iron 3 oxide. You want formulas for everything on your reactant side separated by arrows, everything on your product side separated by arrows. By plus signs. So our chemical formula for iron, we know that it's a metal, it comes straight off the periodic table, is Fe. Oxygen, which ties back into our periodic trends, is one of our diatomic molecules. So instead of just being O, it's going to be O2. That means we have two oxygens bound together, and that's how oxygen naturally comes. And then iron 3 oxide, we've practiced naming, we've practiced making formulas. We know that that 3 in the parentheses stands for the charge on your iron compound. Okay, so your iron is a plus 3. From where oxygen lies on the periodic table, it's a minus 2. And when your charges are not equal, you have to crisscross them. So that is why the 3 has gone from the top of your iron to the bottom of your oxygen, and the 2 has gone from the top of your oxygen to the bottom of that iron. You have to crisscross them so that you will end up with equal but opposite charges. So if you have 2 iron 3s, so 2 iron 3 pluses, that means your total positive is plus 6. If you have 3 oxygens at a negative 2, your total negative is negative 6. Plus 6 minus 6 equals 0. So that means that we have a balanced chemical formula for iron 3 oxide. Very, very, very important because you cannot balance a chemical equation if your compounds are not balanced first. So make sure you definitely do that. And what this is an example of, this formula or this equation that I just read, is an example of a skeleton equation. And a skeleton equation is a chemical equation that does not indicate the relative amounts of reactants and products. So this pretty much just says it's going to show you what is involved, but not how much. Those little subscripts, those 2s and 3s that you see in our equation we just did, are not considered relative amounts. Those are considered amounts within your compound, but not of your entire compound. Okay, so they do not count as our relative amounts. And we'll talk about how to add or show our relative amounts in an equation in a minute. So a skeleton equation you need to think about as like a backbone, a foundation of your chemical equation. You have to have a skeleton first before you can do anything else to it, okay? So you've got to make sure that you have one of those. So on this slide, we are actually looking at the steps for writing a full skeleton equation. So we're taking what we just learned and we're just adding a couple extra steps to it, which are necessary for then writing balance equations. So our first step is what we've been doing to write our skeleton equation. So we take care of that. That's the Fe plus O2 yields Fe2O3, our equation with formulas. And then we indicate physical state. So that's step 2. Indicate physical state of substances. So solid, liquid, gas, or aqueous. Now, solid, liquid, and gas are pretty standard. Aqueous, however, might be a little tricky. We've talked about it in the past, but not nearly as much as the rest, so I'm going to give a quick refresher on it, and that is that aqueous or AQ means dissolved in water. So if I ever say the word solution, or I say in water, so sodium chloride solution, that would be AQ because it's what normally would be a solid in liquid state. So I just hope that you can get that. Usually it will have a telltale sign like that to show you, okay, this is an aqueous compound. And then you just need to make sure you know the physical state at room temperature. If you know it at room temperature, that's the state that we would put. Most of these are pretty standard. If you know what state it is on the periodic table, that's the state that we would put it in, because the periodic table, most of them are written for room temperature, especially if they're color coordinated. And then step 3 is acknowledge any catalyst. And it's pretty difficult. This is the hardest one, but it's also the one that we use the least, because catalysts are hard to recognize if it doesn't say catalyzed by so-and-so. So most of the examples that you will have will tell you that it's catalyzed by something, or I will tell you it's catalyzed by something. And you just need to know that this is a step we don't use very often, but you do need to be aware of it because it does come up. And the idea of a catalyst, what a catalyst is very important for later when we talk about reaction rates. So a catalyst is a substance that speeds up a reaction but is not used in a reaction. So it's neither a reactant nor a product. It's not being created nor consumed. So that means we write it above the arrow. We like for it to be present in the reaction, but not on a specific side. It's like on the fence. So it's good to kind of know what those are and where they're located. And if you look back at 2A, I'm going to show an example for 2A. And the reason I haven't shown it yet is because I actually want to tie in step 3 as well. So Fe solid plus O2 gas yields Fe2O3 solid. So you can see that I have my skeleton equation. I have indicated my states. We know these because iron is a metal, solid. O2, oxygen, we know comes as a gas. And Fe2O3, which is rust, is a solid as well. This is a very fast reaction on its own. It happens in a couple of minutes if done correctly. So it does not need a catalyst, which means our arrow will be empty. It will not have anything above it because it does not need a catalyst to happen. But now if you look down on 3B, I've given you an example that needs a catalyst because it says so. So this example, MnO2 catalyzes H2O2 decomposition. MnO2, which is manganese dioxide, is used to speed up the breakdown of H2O2, hydrogen peroxide. You should all know what that is. You've probably put it on cuts and scrapes before. So when we use it in the lab, it breaks down pretty fast. That's why it bubbles so quickly when it's put on your skin. But sometimes not fast enough. We might get a little impatient. So to take care of that, we add a catalyst to your system. MnO2 is one we use a lot. Another one we use a lot is Ki, potassium iodide. And you will actually see this reaction with potassium iodide over the next couple of days when I do demos of types of reaction. I'll make elephant toothpaste, and it's really fun, really messy. Everyone loves that. I like it. So I really hope that you guys will enjoy that as well. But you'll see this one in action. And you can see that I have put the example underneath, and I have H2O2 aqueous because it is dissolved in water, hydrogen peroxide, and you can tell usually because if you buy it from the store, it'll say like 6% or 4% or 3%. Stuff in the labs usually 20 or 30%. That means 6% of that solution is hydrogen peroxide. The rest of it's water. So that's aqueous solution. It's dissolved in water. So I have an AQ there. Then that is my only reactant because we're breaking it down. On my product side, I have H2O, which we know is a liquid. It's going to stay water, plus O2 gas. You know it gives off O2 because it makes bubbles. And that's how you know it's breaking down. And since we know MnO2 was a catalyst, we have put it above the arrow, which is where it needs to go. Another catalyst that can be used a lot, but I don't want you to get too used to this one because a lot of people think that every reaction is catalyzed by this, but not necessarily, is heat. So a lot of times it'll say catalyzed by heat. System was heated up, stuff like that. That means that it was using heat as a catalyst. Now, yeah, if you heat up most reactions, they will happen faster, but that does not necessarily mean it's considered a catalyst in that situation. So if it says catalyzed by heat, or I tell you, then you would write the word heat above that arrow. Another example is a triangle written above the arrow, and that triangle stands for heat. Remember what I said earlier about us abbreviating everything. So we like to use Greek symbols as well. So that triangle, that delta, means heat. Okay, so these are some examples that I would like us to try that will help you practice writing a full skeleton equation, so including all the steps that we just went over. Once I get through reading these examples, I would like for you to pause the PowerPoint and then go on and try the examples on your own. Once you've tried them, you can continue the PowerPoint video and check your answers on the next slide. So, your examples. Nitrogen gas and hydrogen gas react to form ammonia gas. And I've given you the formula for ammonia. We've talked about it in class, but I don't think we've talked about it enough for it to have really stuck. So here's the formula. This is what you'll use for ammonia gas. The second example. Potassium metal reacts with magnesium bromide to form potassium bromide and magnesium metal. Now here, I really want you to make sure that you pay attention to your chemical formulas. This applies to the first example as well, but not as much as it does in this example. So please make sure you pay attention to your chemical formulas and that your compounds are balanced, because if they aren't balanced, we cannot write a correct full skeleton equation and then later write a full balanced equation. So please make sure you check those. So now, as you practice these, please pause the video. Once you have finished, you can check your answers on the next slide. Okay, so here are our answers. We have, for the first one with nitrogen and hydrogen to form ammonia, we have N2 gas plus H2 gas yields NH3 gas. Now, the states should have been very easy on this one for the sheer fact that I told you the states of all of them in the question. Now, the trickiest part about this is remembering your periodic trend of diatomic molecules and knowing that nitrogen and hydrogen both fall in that category. So they have to come partnered with another nitrogen and another hydrogen. So make sure you remember that's why they come as N2 and H2. Your second example came out to K solid plus MgBr2 solid yields KBr solid plus Mg solid. Here, all your states are the same. That was pretty easy. But the trickiest part is making sure your MgBr2 was correct for your balanced compound. You have to remember that Mg is a +2 and Br is a -1, which is why we have to have two Brs to cancel the positive charge on the Mg, which is why our formula is MgBr2. If you don't have the formula correct, it's not going to be able to balance the way that we need it to. Now, we've practiced writing full equations, and what we need to do is take those full skeleton equations, those full backbones to our reactions, and we need to balance them back out. So, when we do this, the example I like to use is building a bicycle. And when you think about a bicycle, you got to think about all the parts that go into making a bicycle. And some of these parts are pretty important, like the wheels, the frame, your handlebars, your pedals. All of those go into, and I know there are other parts, some that people think are more important than the ones I've listed, but just humor me for this example. All of these parts come together, and that's how you make the bike. That's how you put the bike together. If you don't have these parts, you don't have a bike. And now that we know what it takes to make a bike, we need to think about the amounts that it takes to make a bike. So when we look at our frame and our handlebars, you only need one of each of those. If you have one frame and one set of handlebars, that's all you need. You don't need multiple sets to make a regular bike. But when we look at pedals, you have to have two of those, one on each side, because if you only have one, you might be able to pedal in a circle, maybe. And wheels, if you don't have two, then you don't have a bicycle. That's how it got its name. So, let's look at the formula here that I've written down. And this shows in chemical formula terms, as chemically formula as I can make that example, that you need one frame, which is the F, plus two wheels, which is why that 2 is out front, and I'll explain why they're highlighted and underlined in a minute, plus HB for my handlebars, one handlebars, and then 2P, two pedals. When you put them all together, you see that those big 2's that I have become subscripts, and this formula, FW2HBP2, is the formula for a bicycle. And the reason we know this formula is because we know it takes two wheels, we know it takes two pedals, and the rest, it just takes one of those. And we have to make sure, by the law of conservation of mass or matter, that we have the same amounts on both sides. So if I look on my left and right, I have one F, two W's, one HB, 2P, 2P. So we are a balanced chemical equation. And that's what we're doing here. We're balancing these equations. And this is where it starts to get kind of fun. Once you get through writing your formula out and making sure your compounds are balanced, now you get to work through it and see if you can make everything balanced the way it's supposed to. Sometimes it's very easy. Sometimes you don't have to do any work. Sometimes it's very difficult, which is why I suggest when you do these next coming examples and you do the website examples that I've got and watch some videos and stuff, I expect you to try them in pencil so that you can erase things in case you mess up. If you end up getting a really tough one where you actually have to go through and balance one way and then double your numbers and balance another way, all this stuff. You would see this in class tomorrow with pencils and worksheets, and I would expect them to be done in pencil because if you do them in pen, you're going to get frustrated because you're going to have to mark them all out. So we're going to work on that a lot tomorrow in class. So I said I was going to explain why these 2's are bolded, underlined, highlighted, all that stuff, why they're so important. And that's because they're what we call coefficients. This is a very important term that you need to know, so make sure you have this definition down. Coefficients are small whole numbers that are placed in front of a formula in an equation in order to balance it. So coefficients are not placed where subscripts are. Coefficients are written out front of whatever needs to be balanced. And I would ask that you write it and you underline it. On some worksheets, I may go ahead and help you out and give you one of your coefficients, but I want you to underline what you add so that I know you added it. Okay, so please make sure you underline it. You don't have to bold it or highlight or anything, but just make sure you underline it for me. And when you use coefficients, so we plug them in on that example, that chemical formula that we have up top, this is what is included in a balanced equation. This is what makes a balanced equation different from a skeleton equation. Because a balanced equation is when each side has the same number of atoms of each element and mass is conserved. So we have added these coefficients to balance everything out, and that's what constitutes a balanced chemical equation. So we're going to practice a couple of these after we go over the steps. And since this is a PowerPoint, I don't have an active slate or anything like that. I can't work them out in front of you. I actually have pictures of me working them out as well. So you'll be able to see those in a minute. The steps to balancing is really not hard. You have to be able to do all the steps of writing a full skeleton that we did earlier. So you've got to be able to write the skeleton, add the states, and to check for catalysts. So you've got to make sure you can do all that. Once you've done that, you add coefficients in to balance so that your equation obeys the law of conservation of mass. Told you I was going to bring this back up. Here it is. And the way you can do this is using a balancing table. And I'll show you how to use those. They're not hard at all. They actually help a lot. I had to use them when I started doing these. I still use them today, and I've been doing this for years now. So please make sure you practice using balancing tables. Yeah, it's going to take some paper, but you can write multiple tables per page as you're working these out. That's completely fine. If I give you room on your worksheet, you could do it there. If not, you might just want to have some extra paper close to you so you can work on those. But this is where I start to have a lot of fun, because this is where I can really tie into my nerdy math side, because I get to balance things out and try to figure out how to get both sides balanced and see where I need to change things, add things, multiply things. It's very, very fun. So if you like puzzles, you should like balancing equations. So here's an example, and I like that I'm using this one first because it shows pretty much how to set up a T-table without really having to use it too much. And we're going to go through this example, and then the next one we'll go through together as well. So this example says carbon plus oxygen reacts to form carbon dioxide. So we're taking carbon, reacting it with oxygen to form carbon dioxide. So our first step was writing our full skeleton equation, which is what I have here. So we've got C, and we know carbon comes as solid state, plus O2, remember oxygen's diatomic and it's a gas, yields CO2. So carbon dioxide, remember if it's a molecule covalent compound, those prefixes mean how many you have there. So carbon dioxide, CO2. So here is our full skeleton equation. No catalyst, didn't mention one, so we don't have to worry about it. So your next step is adding coefficients to balance. So this is what a T-table looks like. All you need is your first or your second and third column labeled reactants and products, and then down the side of your first column, you just list all of your elements present. And you'll see as we practice these a little bit more, certain things you can keep together. Your polyatomic compounds that you know about, some of those you can keep together if they stay together on both sides. If they do not stay together on both sides, you need to break them up. But here we can see I don't have a column for CO2 because I have one already for C and one for O. So you do not need to worry about a column for CO2 because we're just balancing our elements here, okay? So if you look here, C and O are the only elements present in our equation. So what we do is in our C row, all you have to do is write how many C's you have in the reactant side, how many C's you have in the product side. So we have 1 on our reactant side, 1 on our product side. Good. O, we have 2 oxygens on our reactant side. Remember, it's O2. That subscript tells you how many you have right now there. And then on my product side, it's O2, so I have 2 there as well. If you look at this, you can tell that I already have a balanced chemical equation because my reactant side is equal to my product side for both compounds. So you get a big old check mark on this one because it was really easy. Everything's taken care of. Everything's balanced on both sides. So let's try another one and we'll see how this one goes. Hydrogen gas plus oxygen gas to form water vapor. Now I did specify state here, so you've got to pay attention to that as well. First step, full skeleton equation. H2 plus O2, both of them are diatomic and they're in gaseous state, yields H2O. If I say the word vapor, that means gaseous state. So we don't have a symbol for vapor because all vapor means is something that's normally in liquid state put into gaseous state, so you just have to put a gas symbol there, and that's fine. So this is our full skeleton. It's taken care of. It's done, which is great. So now we have to balance. We've got to show our T table, or our balancing table here. Well, when we look at this table, you can see, okay, awesome, my hydrogens are balanced. They're taken care of, no problem. Oh, wait. My oxygens aren't balanced because I have 2 on my reactant side and only 1 on my product side. So when you look at this, is it as easy as the last one? Nope. So we have to do a couple extra steps here. And this is where I'm going to show you pictures of how to work through your balancing table. So let's see. First, we have our set balancing table. This is just that example that I just showed you. We can tell that things are not balanced because our numbers are not all equal to each other. And what you would like to do first is to always try to balance really whatever needs to be balanced, because here you only have to balance 1 to start off with. And I would take whichever element you have, if you have multiple, that is not balanced, but one of them has a 1 present, I would do that first. So you see here how if hydrogen wasn't balanced and oxygen wasn't balanced and oxygen had a 1 like it does, I would try to balance those out first because then your numbers might be a little easier to handle. So what I did was I said, okay, oxygens aren't balanced. I need to work on balancing those. And the only way I can do that is adding coefficients. I can't change subscripts. I can't change any of that. I can only add coefficients. So if you look up in my actual equation, I have thrown a 2 in front of H2O. If I throw a 2 in front of that H2O, bing, bang, boom, it takes care of my oxygen. So you can tell I've marked it out and I've wrote a 2 there. But you need to make sure you pay attention. When you add a coefficient in front of a compound, it affects every element in that compound, not just the one you want it to affect. So because of that, and I know this picture is blurry, I'm sorry. We didn't only change our oxygens, but we also changed our hydrogens because that 2 is out in front of H2O. So it goes on the H, it goes on the O. Since we had 2 already, and then we stick a 2 out front, you multiply everything here. So that means I now have 4 hydrogens on my product side and 2 on my reactant side. Well, geez Louise, I'm still not balanced. So I need to take one more step and put a 2 out front of my H2. Now, since it's out front of my H2, it only affects my H2. That plus sign between the H2 and the O2 means that no coefficients are affecting the other. Okay? That's like an ending sign for your coefficient power. So since we do this and we stick a 2 out front of my H2, you multiply again, and that gives us 4. So I'm going to go on to the next slide. We can actually look at the new T table typed out because it's neater than my handwriting. I'm sorry. And here we have our new T table. So if you look at this, on my products and reactant side of my hydrogens, I have 4 on both. Good. It's balanced. And on my oxygen side, I have 2 on both sides. Awesome. It's balanced as well. So to make sure we take account of this, I have rewritten or retyped the formula with the coefficients in there underlined and bolded. So this is now a balanced chemical equation, which is great. So you guys have actually worked through and balanced your first chemical equation with me, which is awesome because I know you did great. Okay, so we've gone over balancing equations and all of the steps you need for those, which are very similar to full skeleton equations, and we need to make sure that we can go over and try these. So the examples that you tried earlier with the ammonium gas and the potassium and magnesium bromide that you did for writing full equations, I actually want you now to try to balance those. So if you will go back and look at those examples, you've already taken care of step 1. Now you just need to balance. So if you will look at those and pause this video, once you've tried them and you think that you've got them correct and you've used the right table, you can continue on with the video and check your answers. Okay, so here are our answers for our balanced full equations. As you can tell, I've highlighted and underlined the coefficients that we had to add to balance. So for the first one, we have N2 gas plus 3H2 gas yields 2NH3 gas. So the easiest way to start this is realizing that you have 2 nitrogens on one side and 1 nitrogen on the other on your product side. So you need to balance those first. Once you've balanced your nitrogens on the product side, you can then see that now instead of 3 hydrogens on my product side, I have 6. So I've got to go back to my reactant side and balance that back out. And the way that you need to do that is by adding 3 more H2s to your reactant side. So by doing this, you multiply that 3 by the 2 on H2, and that will give you 6 hydrogens on the reactant side, balancing your whole compound out. Now your next example, you just do pretty much the same thing. You see that everything is balanced except your bromines from the get-go. On your reactant side, you have 2 bromines, and on your product side, you have 1. So the way you balance that is by multiplying your compound on your product side by 2. That'll balance your bromines. Then you see, okay, well that changes my potassium as well because it's bound to the bromine on my product side. So I must have to multiply my potassiums on my reactant side by 2 as well. Now, these are some extra links that we read through, listened to, practiced in class. These are things I want you to still practice outside of class or to read or to watch because they are very, very helpful, and they're going to give you more practice so that when you practice these later and then we get into moles and stoichiometry, this is going to be second nature to you. You're going to do great at it. I know you will because you're awesome. So I just hope that you use these to your advantage. The first link, Easy Calculations. This is just another text to read about how to solve these. Easy Calculations is a really good website to use if you are looking for a quick synopsis on how to solve certain equations. And this one was really, really good to read. There are a couple differences here, and it's just due to format, not due to content differences. So instead of on their T table where I wrote reactants and products, they say left-hand side, right-hand side. And just because of the format of the website, they did have to end up putting equal marks on some of their reactions instead of arrows. So don't pay attention to those. Just think that they're arrows. And make sure you check too for the subscripts. If you see a big number in the middle of a compound, that's supposed to be a subscript, not a coefficient. Coefficients only go out front, but sometimes formatting issues happen and we don't catch them. I just want you to make sure that you pay attention to that. So please check that. For my musical learners out there, the second link actually goes to a video that sings a nice, cute little song about balancing equations and why we do it, how we do it, stuff like that. And it's actually set to that song Cups. If you've heard that song, I'm sure you have. I'm sure you've watched Pitch Perfect, so you know the song. And it's actually really cute. It's got some good information in it as well. So I would like for you to watch that. I'm a very musical learner, so if I can set something to song, I remember it a lot better. So I ask that you check that out if you're the same kind of way. If not, it'll give you a good laugh. So you can make sure you check that out. And then this last website is one that we will actually use in class, but if we don't have a lot of time in class or you're wanting to practice the worksheets more while you're there with me, anything like that, this is something very good to try at home. When you have your Chromebooks, you can only run HTML5. You cannot run the regular versions of these because you have to download them and you're not allowed to do that on the Chromebooks. So run the HTML5 version. I've given you the link to the HTML5 version. So that shouldn't be a problem. You shouldn't have to change that. But just make sure that's the one that you're on. And this is PhET, which is a really, really good simulation website for physics, some biology, chemistry, some math. It's really good. They've got great simulations. And this one for balancing chemical equations is actually really fun. The first part of the website, I'd like you to practice because it'll come up on a screen for practice and games. I'd like you to do practice first just to warm yourself up to it, to see how you use the simulation to answer these questions. Then go ahead and play some games. See how many you get right. You get 2 points per question on easy. I tried it yesterday and it was so much fun. So I'd really like for you to try those and then see how difficult you can do. So it was like easy, medium, hard, something like that. And I really want to see how well you can do. Now, I don't expect you to be able to do some of the hard ones right away, but after practice, I think that you'd be able to manage it because it's really fun and you guys are going to do great at it. And that is the end of my presentation. So I really hope you took something from this. I hope you read and watch and play on these websites and ask me any questions that you have. Thank you.